Hi everyone, this is Mr. Bowman, and in our last lesson we started talking about the idea of integrals. Accumulation of rate of change functions is what it was called. What we're going to do now is we're going to move closer to this idea of how we evaluate integrals. So in the examples in the previous section, they were chosen so that we could use geometric formulas like the area for a rectangle, the area for a triangle, a trapezoid, etc. Most of the time, we do not have situations like that. Most of the time, we have situations like the one you see here, in which we have a continuous function, and we have to figure out a way of finding the area between that function and the horizontal axis. So we're going to talk about something that's often called the rectangular approximation method. And let's start with this example. So here's the rate of change function for this situation given right there. And it tells us that at this particular situation, the manager can expect this number of customers per hour. That is clearly a rate of change. On the horizontal axis, we have hours. So when we find the area between the curve, the continuous function, and the x-axis, we will have the change in the total number of customers. So what we could do is we could estimate the area between the curve and the x-axis. And one of the ways we could do that is by saying, oh, at 2-hour increments, we could find the height of the curve. So at 6 a.m., and by the way, the horizontal axis is hours after 6 a.m. So 6 a.m. would be time 0. At 8 a.m., at 10 a.m., at 12 p.m., at 2 p.m. And visually that would look something like this. At 6 a.m., we have 240 customers. That's over a 2-hour interval. So I'm going to draw a rectangle there. At 8 a.m., we have 260. So that would be about right here, and I'm going to draw another rectangle that is 2 units wide. And I'm going to keep doing that at 10 a.m., which is 4 hours after 6 a.m. We have a height of 200, so that's about right there. Make the rectangle 2 units wide, and then one more time at 12 p.m. we have about 120, and we're going to make the rectangle 2 units wide. And from this table, you can see how many customers per hour were at that particular x value. So it gives us the height of the rectangle, and as you know, we can find the area by multiplying the length times the width. So 240 times 2 is going to give us 480. 260 times 2 is going to give us, what, 520. 200 times 2 is going to give us 400. And 120 times 2 is going to give us 240. And if we add those all up, we can get an estimate. It's not the exact value, but we can get an estimate for the total area between the curve and the x-axis. And this would estimate the change in the number of customers over that time interval from 0 to, let's see, 8 hours after, so that would be 2 p.m. Clearly, in this case, it appears to be an overestimate because of this area up here, and that area up here, and that area up here being more than the area between the function and the x-axis, even though we are underestimating, which I will highlight in blue, over that part right there. So this would be considered what is called a right rectangular approximation, and that is because we are using the right-hand side of each rectangle to establish the height of that rectangle. We can actually do a left-hand side rectangular approximation, because we're using the left-hand side of the rectangle to do that approximation for the height. We can use a right rectangular approximation, or we could even use a midpoint. So one of the things we can do is we could also say, you know what, we want to have a better estimate. So think for a minute about how you'd have a better estimate. One of the ways that you could have a better estimate is to make the rectangles more narrow. And by doing that, we get closer to the actual area under the curve with our rectangles. And we are still using the left-hand side of the rectangle to establish the heights of the rectangles. And we would now take those heights, which are indicated with the red dots, and multiply them by the widths, which are 1 hour. And then we would add those all up, and we could get an approximation for that. And you will see down here that we have an approximation for that. And we can basically find that approximation by finding the height of the rectangle, evaluating the function at the left-hand sides of those rectangles to establish the height, and then multiplying it times the width. And since each of these widths are 1, I'm going to highlight in green, those are the areas of each of those rectangles. And those are an estimate for the area between the function c of t and the horizontal axis. And if we add those up, basically we get the height of the function at each x value times the width of the rectangle. We add all those up, which is what this sigma notation tells us. We would get a total change in customers of 1,570. So that's the basic idea behind using rectangles to estimate the area between a function and the horizontal axis. We're going to do an example here where the rectangles are not drawn for you, and we're going to use Desmos to help us out with that. So we have this piecewise function, and this piecewise function represents the rate of change of the concentration of drug in somebody's bloodstream. And the first part of that function, I'm going to highlight in yellow, occurs when somebody is taking the drug. And notice the rate of change from 0 to 20 days is positive, so that means the amount of drug in their bloodstream is actually increasing. And then the second part of the function, which occurs from 20 to 30 days, is a negative rate of change, and that indicates that they've stopped taking the drug, so the amount of drug in their bloodstream is decreasing. So let's see what they want us to do with this. I'm going to highlight these here. There's the yellow portion of the function and the blue portion of the function. And it says in part A, use the model and 10 right rectangles. So use the model and 10 right rectangles to estimate the change in the drug concentration in the bloodstream while the patient is taking the drug. Okay, so two things there. 10 rectangles, and they want us to use the right-hand side of the rectangle. And they want us to do it while they're taking the drug, so from 0 to 20 days. So to make this easier, we're going to jump over to Desmos here, and we're going to have Desmos help us by illustrating these rectangles and finding these areas for us. Okay, so here's what I have. I have the piecewise function, and this is nice example of how you can do a piecewise function. So if you look at the very top, it says m of x is equal to 1.7 times 0.8 to the x, and then it puts those curly brackets, and it says this is the rule for x from 0 to 20. And then right below that, I created another function, t of x, and you can see it's different. It's negative 10.21 plus 3 times the natural log of x, and that applies for x from 20 to 30. So what I want to do is I want to illustrate with right rectangles, and if we were doing this by hand, we would just draw them in by hand. So you can see the dots every 2 units, because 20 divided by 10 is 2, so our rectangles need to be 2 units wide. And they need to be on the right-hand sides of the rectangles. So I'm going to show you what this looks like when we throw the rectangles in there. You can see in this case that the area of our rectangles is going to be less than the area between the function and the curve. So we're going to have a bit of an underestimate. So how would we find the total area of those rectangles? Well, we would make a table, and I can show you how to make a table, and I would create the x values at the right-hand side of each rectangle. So since I wanted to use right rectangles, I would use an x value of 2 there. And to establish that height of that first rectangle, I would evaluate the function at an x value of 2. So that's what I did in this first row. x1 is 2. When x1 is 2, y is 1.088. So that first rectangle has a width of 2 and a height of 1.088. So if I took 1.088 and doubled it, length times width, I get the area of the rectangle. And all I did here in this third column was take the second column, the function, 1.7 times 0.8 to the x, and I multiplied it by the width. It's doubled. So now I could take my calculator and I could add up all these numbers in this column, and that would give me my right rectangular approximation for the area between the function and the x-axis from 0 to 20. So I know we didn't actually add all those up, but we could. We're going to go to part B here, and I'm going to show you how to do part B by hand, basically, even though I would use Desmos to help me with it. So it says, use the model and the right rectangles of width 2 days to estimate the change in the drug concentration in the bloodstream for the first 10 days after the patient stops taking the drug. So basically, we are going to create 10 rectangles in this region right here, where the right-hand side of the rectangle establishes the height for us. So we're going to use x values of 22, 24, 26, 28, and 30. And then we are going to find the heights using m of x for those values. And that is the blue function. So we could easily jump back over to Desmos, and let's do that. We'll create another table. I'm not going to draw the rectangles here because that's actually a little bit harder than you would expect. So we're going to add a table here, and in our table we're going to do x2 is going to be 22. All right, sorry, I'm trying to get this to work for me. 22. My keyboard is not working. 22, 24, 26, 28, 30, and then I do not want 32 in there, and my y2 is going to be equal to the function, which is t of x, so negative 10.21 plus 3 times the natural log of x2 is what I need to call that. And I actually don't want to type in an equation. I just want to type in an expression, and that should, got to change that to an ln, and there we go. So that's the height of the 5 rectangles. And the width of those 5 rectangles are all 2, so I have to multiply those by 2 and add up those negative values. And when I do that, it's going to give me the answer to part B. And then finally in part C, it says combine your answers to parts A and B to estimate the change in the drug concentration in the bloodstream over the 30-day time period. So the first answer, part A, the area between the function and the x-axis is going to be positive. And in part B, the area between the function and the x-axis is going to be negative. So when we add those up, we'll get the final result. And that's how we do rectangular approximation methods. So just to illustrate, this first example here would be a left rectangular approximation method. The second example, so sometimes it's called LRAM, The second example would be right rectangular approximation method. Sometimes it's called RAM. And then the third method would be a midpoint rectangular approximation method, and that is called MRAM. And remember, that's only to establish the heights of our rectangles. You have to figure out what x values those occur at based on which method you're using and how wide you want your rectangles to be. So in the example we're looking at right now, our x values would be 0.25, 0.75, 1.25, and 1.75 to establish the heights of our rectangles. So this is where we're gonna end this lesson today. We'll talk more about this idea in the next lesson and connect this to the official definition of the integral.